FlashKDA, Flash Kimi Delta Attention is a high-performance kernel built on top of the Cutlass library. It targets recent NVIDIA GPUs with compute capability 9.0 and higher and works with CUDA version 12.9 and above. The package is also compatible with PyTorch 2.4 or later. To install FlashKDA, clone the repository from GitHub. First run git clone https GitHub MoonshotAI FlashKDA git FlashKDA. Then change into the directory, update submodules, and install the Python package. cd FlashKDA git submodule update. Init recursive pip install v. No build isolation. By default, the build uses the CUDA device that is currently active and compiles code for that architecture. If you need a wheel or continuous integration image that supports multiple GPUs, set an environment variable that lists all required architectures. For example, FlashKDA CUDA arches equals all pip install v. No build isolation. You can also pass a comma-separated list of architecture codes such as Nanetione or 100, but the simplest option is auto, which compiles for the device in use. FlashKDA is designed to be an optional backend for the Flash Linear Attention library, which implements a fast linear attention mechanism. Once installed, the Flash Linear Attention code automatically dispatches to FlashKDA for the chunk KDA operation, but you can override this by setting an environment variable. The integration details are shown in the pull request on GitHub. To use FlashKDA within Flash Linear Attention, you first need to install Flash Linear Attention with a version greater than or equal to 0.5.0 pip install u Flash Linear Attention. Then, inside a PyTorch inference mode context, call the chunk KDA function from the FlashKDA module. A typical snippet looks like this. Import torch and chunk KDA. Run the entire block under torch inference mode, so that gradients are not tracked. The function signature accepts tensors for query, key, value, gate, beta, and other optional parameters. For example, with torch inference mode, out, final state equals chunk KDA q equals q, k equals k, v equals v, g equals g, beta equals beta, scale equals scale, initial state equals h0, output final state equals true. Use gate and kernel equals true. Use qkl2 norm and kernel equals true. Use beta sigmoid and kernel equals true. Safe gate equals true. A log equals a log. dt bias equals dt bias. Lower bound equals lower bound. Transpose state layout equals true. Q-sequence equals Q-sequence. If you want to disable the FlashKDA backend, set the environment variable FLA FlashKDA to 0. For debugging the dispatch path, you can add a logging configuration at info level. This will print whether the function chose the FlashKDA path or fell back to the Triton implementation and why. Performance benchmarks for this kernel are documented in the repository. The benchmarks show how FlashKDA scales with input size and GPU architecture. Running the test suite is straightforward. From the project root, execute the test shell script, bash tests test sh. Inside the tests folder, there is a file called tests.fwdpy that checks that the kernel produces results that exactly match the reference implementation in PyTorch and the Flash Linear Attention version. This ensures correctness. The kernel API is exposed through the FlashKDA module. The main function, FlashKDA FWD, takes query, key, value, gate, beta, and scale tensors, as well as output tensors and optional parameters. The signature is FlashKDA FWDQ, K, V, G, beta, scale, out, a log, dt bias, lower bound, initial state equals none, final state equals none, Q-sequence equals none. The expected shapes and data types are query, key, and gate tensors are half precision with a shape of batch size by sequence length by heads by key dimension. Value and the output tensor are also half precision, but with a value dimension instead of a key dimension. Beta is a half precision tensor with one entry per head per time step. Scale is a scalar float. A log is a single precision tensor that stores the logit parameter for each head. dt bias is a single precision tensor with a shape of heads by key dimension. It holds the gate bias. Lower bound is a scalar float between -5 and 0 representing the minimum gate value. The optional initial and final state tensors can be either half or single precision and have a shape that includes batch, heads, value dimension, and key dimension. They can also be none to make the kernel stateless. If variable length sequences are used, you should provide cumulative sequence lengths. In that case, batch size must be 1 and the total sequence length is the sum across all sequences. When q-sequence is not provided, each batch element is treated as an independent sequence, and the state tensors are shaped per batch. When q-sequence is provided, the batch dimension is collapsed into a single sequence, and the state tensors reflect the number of separate sequences. For development and debugging, setting up IntelliSense for the CUDA and C++ sources is helpful. Running the script setup clanged.sh will generate a clanged file with the correct repository paths and copy a global clanged configuration file into your user configuration directory. This enables language server features for the source code. If you wish to cite FlashKDA, you can reference the following bibtex entry at FlashKDA 2026, title equals FlashKDA, Kimi Delta Attention, author equals Yushin Chen and Xian Li and Yuchen Wang and Ming Wei, year equals 2026, publisher equals GitHub, how published equals https GitHub MoonshotAI FlashKDA. This concludes the key information about FlashKDA, its installation, integration with Flash Linear Attention, usage, API, and testing instructions.